The number one asks for the elements that can happen, the reaction that can happen, and we can see that we have the B and the E. This can happen because we have our metal. This is the ferritum, as you can see. The part 2 asks for the enthalpy of formation in this case. To solve this problem, remember that this is the enthalpy of a temperature of 298 Kelvin. Now we're going to do the part D. Okay, it's very easy to solve this because you need the enthalpy of formation of products that is in this part minus the reactant. It's a sum. So according to that, we have the next. For C2, we have this value that you can get in tables. For 3CO, carbon dioxide, we have this value that is negative. So, and this is the coefficient, stoichiometric coefficient, as you can see. Now, this is minus the sum of the reactant, that in this case is 3. The KCO3, that is the value of enthalpy of formation of KCO3, plus the enthalpy of formation of alumina. If we solve this, we are going to get this part, that is 527.3, and remember, we need to specify the units. In this case, it's kilojoules over mole. Okay. For the number 3, they ask for the total enthalpy, the change of enthalpy. We're going to use this formula that we have here, and now look at the coefficients. The coefficients are provided by this table, and now we need to do an integration from T1 to T2 from Cp dt. Now we have the delta H, that is 629 of the point of the reaction G, that is this one. It's in kilojoules over mole. And now we want to work this reaction. Look at first of all, the integration is from 293 to 1633. And look at the coefficients. This coefficient is provided by the table. We don't have a C, as I show you, in dt from dt. We got this. Remember, we have to change the units because we're going to go 328,000 joules over mole, and we want to change it to kilojoules. We only divide by 1,000. Now we do the same with the reactions. This is from 293 to 1,633. Okay. We do the respect integral, and we're going to get this value for this product, that is the C2, and we're going to get this one from the CaO. Now, the formula is always the same. It's products minus reactants, as you can see, and we get this value. Now, if forget the total enthalpy, the change of total enthalpy, we use our value that we got plus the delta H that we got respectively in the past exercise from the point G in a temperature of 298 Kelvin. We are going to get 32.5 kilojoules over mole, and we do the same for all the reactions. For the next table, now I'm going to present you the complete table. This is the formulas that we got, the information that we got, and I'm going to show you this. To get the total enthalpy, it's just the sum of all this. As you can see, sum this plus this plus this plus this, etc. Now, to convert to another factor, we have the convert factor. We only have to multiply this number times this number, and we're gonna get this one. Here it's an example that I told you. This is the reaction A. The factor, the convert factor, mole cracker, just cancel, and we got this number. Okay, in the number 6, they ask just for a definition about the calorific value of fuel. In this case, we have this definition. The calorific value of fuel is the quantity of heat produced by its combustion and at constant pressure and under normal conditions. Now, for number 7, they ask us how much fuel do we need in tonnes per hour. Now, this is a simple conversation, and I present you. This is the kilograms. As you can see, this is the ration that we have at the beginning of our exercise. This is extra information. If we do the corresponding operation, we're gonna get this. Look, now that we get this, the kilograms, now we are going to get the energy that is produced by our, or the energy that is needed to produce this crystallization. Now we're going to convert this to kilograms petroleum coal, I guess, and we're going to get this number. But remember, once we get this number, we're just going to multiply this, and we're going to divide it, the tunnel, because we want it in tunnels, and we're going to get this. That is the correct answer, 1.079 tunnels per hour.
Okay, for the problem, for the question number 8, we're going to figure out the phase. First of all, we have to assume that the mass is about, we're going to find that the mass is about 23%. And first of all, we need to change the temperature that we have, that is in Kelvin, to Celsius, because our temperature is in Celsius in this diagram. Now, we're looking for the sum. Now, if we look at the sum, that is about 23%, and we up, we're going to find the phase is more or less about this area, around this area, probably around here and the intersection and this point. So we can conclude, according to the diagram, that the final phase of C2S is C3S plus alpha prime minus C2S. Okay, for the next diagram, they give us this information about the percent about these compounds. So they ask us to shade an area for these elements in a ternary phase diagram. Alright, now with this indicate the up, the CO up, and it start from 0, the KO, there is 0 to 70, and the aluminium, there is 0 to 100. Now if we look at this first, the CO2, this indicator is 44%, so we start here and we indicate that this point is about 44%. Now we trace a line, this part, and for the aluminium there is 4. Look at the arrow, we signal that is about 4 here, we trace a line again, and for the last compound is 70%. It starts from 0 to 70. We'll look for that, and we are going to see there is about this, and we trace a line. Alright, this. So then indicate this little area there is an approximation, and we indicate that the shape is below. In the point number 10, they want to know good reasons about to decrease or increase the petroleum coal. The petroleum coal, there is a fuel used for in this kind of cream for the reactions. Now, a good reason to increase the tons per hour of this fuel is to improve the efficiency of the cream. And a good reason to decrease it is when there is too much sulfur in the content produced in the cream, and it's a good idea to decrease.
So my problem today is to discuss a turbine that takes around 5,000 kilograms an hour of water vapor at a pressure of around 4,000 kilopascals at a temperature of 300 degrees. As you can see right here, I've drawn a diagram of what the system looks like. You have your initial conditions here that should be 4,000 kilopascals, excuse me. And at 1 is your kind of entrance turbine, 2 is kind of between that and the valve, and 3 is the valve. And at the valve, your pressures is 1 atmosphere because atmospheric pressure, and that's at 101.325 kilopascals. The temperature is unknown, and then the velocity is 200 meters per second. And the difference between that is a negative 3 meter decrease. So I'd first like to outline that we have the turbine generates 570 kilowatts of power. And then the heat loss is 135 kilojoules per minute. With that information, I converted the 570 kilowatt of power into joules, which is equal to 2.05 times 10 to the 9th joules per second. And then the heat loss I've converted into kilojoules per hour, which becomes, you turn that, I have the 195 kilojoules per minute, ends up equaling around 8,100 kilojoules per hour. So taking that value, I can now do some conversions. So I want to calculate, so the overall goal is to calculate the temperature, the quality of vapor, and so on. So before I do it now, I want to kind of go after the enthalpy. And to calculate enthalpy, I'm going to, or for the first couple values in enthalpy, I'm going to calculate Q, which right here is equal to the heat loss divided by that flow rate, I guess, of how much water vapor is taken in. So that can be assumed to be 8,100 divided by 5,000, which was how many kilograms an hour of water vapor we are taking in. And that value comes to be 1.62 joules. With that, I will now calculate the work, which right here we do. Hold on, sorry. We will be calculating the work, which equals the work of the system. So how much power is produced divided by that mass flow rate is how my partner explained the process to me. And then that becomes 2.05 times 10 to the 9th divided by that 5,000 number once more, and that equals 408 kilojoules per hour. And that is after I converted this number to joules. So I'll just write it in here. It should be 10 to the 6th, and that comes out to be 408 kilojoules per hour. With that, I can now start to answer my enthalpy problem. And how my partner at ITSM in Monterey explained it to me is there's a couple components of this enthalpy equation. You have a delta, I'll call DH plus DP or DPE plus DKE, and that equals Q minus W, the enthalpy, the change in enthalpy. And that change in enthalpy is what we're calculating. But you also need to focus on DPE, which is the potential energy, and then DKE, which is the kinetic energy of the system. So before we solve for DH, we're going to first go after DPE. So potential energy is just that height drop times the gravity constant. So right here we have 9.8, the gravity constant, times 3 meters. And that comes out to be, well, I'll write this out first. And then that 9.8 times 3 equals around 29.43 joules. Since we have that, and I will next go after DKE, which is the kinetic energy, and we solve that by doing the simple 1/2 velocity squared function, which equals just 1/2 times the exit speed, which is 200 meters per second, subtracting 60 meters per second, which was the entrance speed, excuse me, the 200 meters per second was the exit speed, and that is actually equal to, sorry, that is, yeah, I'll put it rest in the equation. And then you can solve for dH, which turns out to be negative 427.84 kilojoules. Having that value now, you have the change in enthalpy over your system. Not at any point so far. So at the beginning of the process, there was a calculation done through my partner's. He showed me some tables. So we were Skyping, and he was showing me some tables over some enthalpy values at certain pressures and whatnot. And we came to he showed me an understanding of what that enthalpy value was. We'll call it H1. Immediately, it was 2,961.7 joules, and this was based upon the pressure, the temperature, and everything. He explained it to me as some values that you looked up in the back of the book, and then you kind of culminated that into an H term. But now, since we have a delta H, we can find H sub 2, which happens to be 2,534.7 joules. And that is your enthalpy at point, I guess you'd call that point 2, so right in here. And then at point 3, my partner helped me understand that this system was an isothermal system, so there is no there's no work done on the system, or no Q done in the system as well as work. So that's why, because that enthalpy at H3, this point here, is also 2,534.7 joules, just like at H2. And with it being isothermal, we can now answer the question letter A of what the temperature of the vapor is. And from the calculations and how my partner helped me understand is that it is the same temperature as it came in because of that isothermal system. And to understand or to calculate the quality of the value, whether it was there was a number between the enthalpy values, you could look it back up in the book, and we determined that the quality is a mixture combination of water and steam, where you have vapor and liquid, and there's actually a numerical value that was provided that you could calculate. So I'm going to first write it out. You have delta H sub T, it's called the total enthalpy, and then you have 1 minus X, which is that numerical constant you want, times H of F, which is the enthalpy for or H times L, excuse me, for the gas, or for the liquid, then plus X times H sub G, which is the enthalpy for gas, for water. And he gave me values for H of G in the back of his book to be 2,675, and then for H sub L, I was given values of 49 joules, excuse me. Once you plug those numbers in and you do that algebra, including your DH total, you're going to get an X value of 0.93, which I think is how he didn't explain quite well what it was, but I think it is a numerical constant that shows what size. So say you have the water on one side and steam on the other side, it's leaning towards the steam since it's 0.93 almost to 1, which would be then steam, is my understanding of it. So that kind of answers letter B. And then for letter C, since it is it's an isothermal system, and we were unable to determine the thermodynamic state of the vapor at the discharge of the turbine, is because there was not enough info included into the problem. So that was the final answer for C that my partner helped me understand. So that is my basic understanding of this thermodynamic problem. involving pressures and temperatures and so on. So that's it. Thank you.